In this second video corresponding to chapter 18, we're going to talk about heat and heat absorption by materials, which leads to the idea of specific heat and heat capacity. So maybe some of you are familiar with that from chemistry. It's often seen there as well. But let's go ahead and first of all make some definitions. So heat is basically energy. In fact, heat is the energy transferred or absorbed by materials, and it's going to depend on the material and also the temperature difference. A couple units that are used, right, since heat is energy, it's joules, but often people use a calorie or a kilocalorie. 1 calorie is equal to 4.1868 joules. Now, when something absorbs heat, for example, water or other materials, metals like that, the heat absorbed or actually transferred, right, because you could have a water that's losing heat, but the amount of heat that is gained or lost is proportional to the change in temperature, T final minus T initial. The proportionality constant we call the heat capacity. Now, the heat capacity is going to depend on the mass, right? The more mass of water you have, the longer it takes to boil. You have to add more heat to change the temperature. So we also define something called the specific heat, such that the specific heat is the heat capacity, capital C, over the mass. So it's the heat capacity per unit mass, and this is a little c. So Q equals MC, specific heat, times delta T. So in calorimetry problems, this is often what we use. And in fact, the problem you'll see in the homework assignment is like that, using this. People often also talk about molar heat capacity, which is the heat capacity per mole. And 1 mole is equal to 1 Avogadro's number of units or atoms. Right? And Avogadro's number is 6.02 times 10 to the 23. So in the future, we might talk about the molar heat capacity, but not really much in this chapter or in this section. Now you can change temperature to a certain point, right? For example, water, you could go from 0 to 100 degrees, but then as you try to heat it more, it starts to boil and it changes phases from a liquid to a gas. It changes from water into steam. And at this point, what happens is the water temperature stays 100 degrees until all of the water is turned to steam. So if you have a mixture of water and steam, it's always at 100 degrees. You can't go above 100 until you've converted everything into steam. The same thing happens for ice, right? If you want to melt ice, you've got ice mixed with water, it's going to be at 0 degrees. And it takes a certain amount of energy, joules, to convert all of that ice into water, or vice versa, right? To freeze the ice. And so when we have a phase change, we define the heat transfer, heat absorption to be the mass of the ice or the steam times L. Now L is called the latent heat. It's a number that depends upon what the material is. So L sub B is often used for latent heat of vaporization. This would be the heat added to change a liquid to a gas, to make a certain mass of water boil. Now it could go backwards, right? If you're adding heat, you have a positive Q. But if you're subtracting heat, maybe you're taking heat away from the steam, you've got a negative Q. Well, you could lose enough heat that you change all that steam into water, it condenses. Now, latent heat of fusion, LF, is a number or heat, amount of energy added to a certain mass to make it melt, right? So heat added to change a solid to a liquid. So if you have a plus Q again, you want to heat up water or ice, you add heat, MLF amount in order to get it to melt. But you could also freeze it, right? You subtract that MLF to change the water into ice. So anytime you have these phase changes, you'll use a formula of this type. The numbers will be different depending on the mass and what material it is and whether or not it's vaporizing or it's fusing. Okay, so I think the best way to really illustrate this stuff is to do an example here. So I'm going to try to do one that has a phase change in it. So let's just read the problem to begin with. You have a 0.25 kilogram aluminum bowl holding 0.8 kilograms of soup at 25 degrees Celsius. It's placed in a freezer. So now the freezer is going to subtract or take heat away from the bowl and the soup. What is the final temperature if 388,000 joules of energy is transferred from the bowl and the soup to the freezer, assuming the soup's thermal properties are the same as that of water? So basically the soup is like water. So again, what's happening here is we're taking heat energy from kind of stored in the soup and the bowl, and it's transferring to the freezer, right? So the bowl and the soup, their temperature will drop, the freezer will generally increase. Right now, in a real freezer, that heat is added to the outside, so we keep a constant temperature. But let's write down some constants first. So we've got the mass of the aluminum, 0.25 kilograms, the mass of the soup, 0.8. The initial temperature of everything is 25 degrees Celsius. Now the heat transfer is either positive or negative, depending on what you're looking at. If I'm looking at the freezer, it's going to be positive because the freezer is gaining that heat. Specific heat of aluminum, I have to look up in a table. It's 900 joules per kilogram degrees Celsius. Same goes for the water or the soup. It's 4186. Now I put ice here because eventually what happens is the soup gets down to 0, it turns into ice, and then it may drop even lower in temperature. As it goes from 0 to a lower temperature, it's now ice, and we will use this specific heat. And then the latent heat of fusion, since I'm changing from liquid to solid, I'm freezing, I have to use this 334,000 joules per kilogram of water or ice heat of fusion. So I've looked those up in the table, and generally speaking, these types of problems are conservation of energy. Now I put Q lost plus Q gained. I could put really everything that's transferring heat, right? So by Q lost, I mean the heat of the soup plus the heat of the bowl. Now generally it's going to be negative because it's losing heat. The heat gained is really just going to be the positive 388,000 joules because that's the freezer, right? The freezer is gaining that heat. So let's look at the heat lost. Well, first of all, I've got the soup starting as kind of water, and it's going from a T final of 0 minus a T initial of 25. Right? So it's going down from 25 down to 0. Well, then I also have to freeze the soup, and that's going to be MS times LF, actually. This should not be vaporization, it should be fusing. This is going to be a negative. Here I have to choose. Since I'm taking heat away to freeze the soup, I should have that as a negative energy lost by the soup. If I was melting ice, it would be positive, right? But in this case, it is negative. Okay, so once I've got the soup down to 0 degrees Celsius, then it freezes, then I can go even lower. And so I've got an MC delta T for ice. Mass of whatever the soup was, it's now turned to ice, so I use that specific heat. But I don't know the final temperature. I know that it starts from 0 and then goes down to whatever final temperature below the freezing point it gets to. Now I just have one MC delta T for aluminum because it doesn't change phase from, I mean, it's not going to freeze or melt in that temperature range. So I just have mass of aluminum times its specific heat times its delta T. T final minus its initial temperature was 25. You know, plugging in the numbers, I see that this number for the soup going down to 0 is negative 83,720. The amount of heat taken away to freeze all the soup when I calculate this is negative 267,200. Now, I have to kind of distribute here, so I get from the MSCI's TF, I get 1686.4 TF plus 0. Then I get a 225 TF from MALCL TF. And then from MALCL times negative 25 degrees Celsius, I get this negative 5625 joules. Now when I add all of these numbers together, right? I get a negative 356,545. Now that's a good thing because it tells me since it's not bigger than 388, there is enough heat to melt, or sorry, to freeze all of the soup and then take it to a lower temperature. Let's say I got like 400,000 here. Well, then I would know there is not enough heat being transferred to the freezer to actually freeze all the soup here. So I got to kind of watch the numbers a little bit. But I've just added numbers. I get this for my heat loss. Now again, my heat gained is 388,000 joules going to the freezer. So I just add up my heat loss plus my heat gained and set that equal to 0, right? It's kind of like the loop rule in electric circuits. Your heat lost plus your heat gained is 0 around any cycle or in a closed system. Voltage gains and losses around a closed circuit are 0, just all about energy. But at this point, it's just a matter of mathematics. So I'm going to solve for TF, right? Add these over together and bring them over and divide by the 1911.4, and I get a final temperature of negative 16.5 degrees Celsius. So that's the final temperature that everything comes to, the soup and the aluminum bowl. So again, the basic idea here is conservation of energy. I'm going to use Q equals MC delta T for any temperature changes, ML for any phase changes, but generally speaking, all of the Q's of everything in the system, lost or gained, have to add up to 0.